Consider a continuously operating coherent bpsk receiver with a data rate of 8.6 kbps. The digital waveforms are S1 of t equals 6.2 cosine of 3589 t millivolts, and S2 of t is minus 6.2 cos 3589 MV. And the single-sided noise power spectral density is N0 equals 10 to the minus 11 watts per hertz. Assume that the signal power and energy per bit are normalized relative to a 1 ohm resistive load. What is the probability of bit error P sub E experienced by the bpsk receiver? Express your answer as a value of x, where P sub E equals Q of x. Okay, so we've been given some values beginning with the bit rate, which is also equal to the inverse of the bit duration, and that is 8.6 times 10 to the 3 bps, and the bit duration is going to be the inverse of that, and it's 1.163 times 10 to the minus 4 seconds. We've also been given the power spectral density of the noise, N0, which is 10 to the minus 11 watts per hertz. So we go ahead and calculate, beginning with the amplitude, which we are given as 6.2 millivolts. It's also given by the square root of 2 EB divided by TB, where TB is the bit duration. So we could use this relation to obtain the value of EB. That's what we're interested in order to progress. So we have EB, which is the energy per bit, is equals to the amplitude squared from this multiplied by the bit duration divided by 2. So our amplitude is 6.2 times 10 to the minus 3 volts. Then you square that, you get 38.44 multiplied by 10 to the minus 6. Then you multiply by the bit duration divided by 2. Bit duration over here divided by 2, and you end up with 2.235 times 10 to the minus 9 joules. And we are given our PSD, so from that we can obtain the probability of error as probability of error P sub E is equals to Q of 2 square root of 2 EB divided by N0. And we basically replace those values over here. 2 multiplied by the bit energy, you have it over there, then divide by the spectral density of the power spectral density of the noise, which is 10 to the minus 11. And it's important that all these should be maintained in their SI value so that you do not get the wrong values. And you get Q of square root of 447, which is the Q of x. X in this case is the root of 447, which is 21.14.